trend in RTL verification, bug localization, scan chain based methodology, GA based test generation. In this paper, new trend in RTL verification is introduced. This includes bug localization, scan chain based methodology, and GA based test generation. The manual bug localization in hardware description language. Each user design is a time-consuming process. Therefore, there is an increased demand for an automated techniques that can speed up the localization process. In this paper, a code coverage-based method is proposed to rank suspicious code according to its probability of containing bugs, which may result in a significantly reducing the debugging time by starting the first candidate bug location. This method is different from the former method for error localization, such as the assertion-based method, which are suitable for the large design edge method as a simulation-based techniques and suitable for a large design. Our results show that our method can detect errors in large design up to the several thousand lines of RTL code in a few minutes with a high accuracy compared to the time consumed in hours using manual bug localization with a success rate of 100%. An online alter-level scan chain methodology is proposed to reduce debug time, effort, and accelerate IP emulation. Runtime changes the values of the signals of the IP duration. Execution time can be done by the proposed scan chain methodology. A utility tools was developed to help ease this process. Our experiment shows that the area of red is neglected compared to the gain performance benefit, but the design requires more compilation time. The design a main challenge in using constraint random testing. CRT is what that manual analysis for the coverage report is needed to find untested scenarios modifying the test cases to achieve 100% coverage. We need to replace the manual effort by an automatic method or a tool that will be able to extract the coverage report, identify the untested scenarios, add a new constraint, and iterate this process until 100% coverage attained. In other words, we need an automated technique to automate the feedback from the coverage report analysis to test generation process. In this paper, the implementation of this automatic feedback loop is present. The automatic feedback loop is based on artificial intelligence technique called generic algorithm. This technique accelerates coverage-driven functional coverage verification and achieves the coverage closure rapidly by covering uncovered scenario in coverage point report. The introduction. A functional verification is required process to ensure that the design is occurring with the specification. Due to the increasing design complexity of SSS designs systems, the cost of functional verification has significantly increased. According to the ITRS, verification process is now considered a bottleneck as it consumes up to 70% of the design cost. In order to keep the production cost low, it's required to detect bugs as soon as possible. This work targets localization of functional errors. While there are a lot of verification methodology for error detection in RTL designs, there are fewer work for debugging the error, which includes localization and correction stages. Moreover, most of related works are concentrated on gate-level error localization and are applied to the small designs. Here, we are focusing on the RTL level and large designs, detecting locating the source of the anomalous behavior in large and complex RTL design is challenging. In this paper, we present a novel approach for localization methodology to address this challenging using information from regression that result about the failed and passed test cases and number of statements executed by each test. The idea inherited from the software domain. Moreover, we present a proof of concept for this idea using a Verilog-based case study. Simulation-based verification scheme of the large sophistication intellectual property is considered a time-consuming process. Mainly, there are two famous methods to help accelerate the simulation process and reduce verification time: hardware acceleration and hardware RTL emulation. The RTL hardware accelerator solutions are based on the using application-specific ASICs, and each contains specific processors and memories. The RTL hardware emulators are based on using FPGAs, where the designer synthesized into a gate-level list. However, most hardware emulator does not provide easy debugging capability at runtime. In this paper, a scan chain scheme is proposed to reduce debugging time. The proposed method provides an internal glue block, which automatically replaces to any signal with mux and extra input, so that at long time, if they enable this method, we can replace any internal signals by forced one to use it for debugging. The efficiency of the verification process is proportionally to achieving the coverage goals and the less simulation time. Many different test data generation methods like random test data generator have been proposed in the literature. In this work, the verification process problem will be considered as optimization problems. GA is proposed another method for test generation to help reaching 100% functional coverage in less time than a conventional method. The rest of this lecture is organized as follows. In Section 2, bug localization scheme is presented. In Section 3, scan chain-based methodology is introduced. In Section 4, J-based destination scheme is presented. Conclusion are given in the Section 5. The RTL bug localization. In this section, the proposed methodology of RTL bug localization is given in Section 2. A results are discussed in Section 2b. A proposed methodology. Given a set of statements for which an HDL design exhibit incorrect behavior, the object of the design debugging is to find the highly candidate statement of the may be responsible for this incorrect behavior. The failing of the passing test cases are used to find the bug localization. To find the bug location. If the statement is executed by more than two failing test cases, though this statement is more likely to have the bug. So they run complete regression suite until the coverage is 100%. Then they extract the needed information about the past and failed test cases and obtain a list of design statements executing by each test. The proposed methodology is shown in Figure 1. An example to show how our proposed method works and is shown in our Table 1, where we assume that our DUT has only one bug to the only one incorrect statement, and we have the 10 test cases to test in each behavior. From Table 1, the left column shows how each RTL statement is executed by each test cases. Either it is failing to or passing. On entry 1 indicates the statement is executed by the corresponding test case, and an error 0 means it is not executed. The most right the column shows the execution result with an entry 1 for failed test cases and an entry 0 for testing cases. For passing test cases, if a statement is executed by a successful test case, it's likely of the containing a bug is reduced. The weighted probability is used to indicate more successful execution imply less likely to contain the bugs. So the suspiciousness of each statement, the number of the failed test cases that execute it, and the number of the successful tests. And we will choose the maximum value of the start with, that is, a large length. The proposed methodology for automated bug localization figure is shown in Figure 3. B. Experimental result. Experimental result show that the proposed method can detect errors in large region up to several thousand lines of RTL code in a few minutes, with the RTL accuracy compared to the time consuming in hours using manual bug localization. Here, we only localization the error, not correcting it. Other experiments are done and more about to observe the effectiveness of our methodology. We insert the errors in our part of the code of the complex RTL design, and we applied our methodology to a located error. Table 2 reveals some result where it is clear that our methodology reduced the time needed to localize the bug significantly. The effectiveness of this methodology varies for different design bugs and test cases. Here we assume that we have a rich and correct test cases. The Figure 1 proposed methodology for automated localization. Table 1 is a motivational example to describe the proposed methodology. Table 2 is bug localization time using the proposed methodology versus manual debug in a complex design, which contained more than 5,000 lines of RTL code. The proposed RTL level scan chain methodology. RTL simulation provides a system SoC verification with the full debugging capabilities, but its disadvantage a low speed simulation for complicated RTL design. By using FPGA-based RTL emulation, we can have a high-speed simulation, but it's not easy to debug it because it has a poor capabilities feasibility. So the other solution provide full debug capabilities such as RTL emulator. But the offline debugging method needs to recompile the whole design, which slows the verification process. In this paper, we propose an online alternative scan chain-based methodology is proposed for accelerating IP emulation debugging time at runtime. This method provides internal glues block which automatically replaces any signals with the mux next trust input. So at runtime, if we enable this method, we can replace any internal signals values via forced one. Our experiment showed that the area of red is neglected compared to the gained performance benefit. Conventional emulation flow versus the proposed scan chain-based emulation flow is shown in Figure 2 and Figure 3 respectively. To illustrate the proposed method, we assume the example shown in Figure 3a, where out is a non-blocking sign a plus b and multiply c, where the c is a predetermined value that we want to change it at runtime. We compile the designed runtime emulation. If we want to change the values of the C, we have to recompile the whole design. Sometimes it takes a very large time depending on the complexity of the design. So here we propose to use the online RTL level scan chain methodology to be able to change the value of the C at runtime without recompiling the whole design, which basically accelerate the emulation debugging time. We will create a utility tool that instantiates glue and logic and with a lag definition of the RTL file. And the glue logic is the neural connection which puts the input into the output as depicted in Figure 3b. So the designer can change the value of the signal at runtime. It will be automatically auto-generated for the registers defined in the design. Our experiment showed that the area of red is neglected compared to the gained performance benefit. The proposed emulation flow, online flow, the statistical test bench methodology, scan chain methodology, detailed and simplified. The Figure 3 is normal design example and proposed scan chain methodology for design example. Next is GA-based proposed methodology. The GA is heuristic experience search and time efficiency learning and optimizing techniques that mimic the process of the natural evolution based on the Darwinian paradigm. Thus, genetic algorithms implemented the optimization strategies by simulating evolution of a specified species through a natural selection. Each cell of the living things contains a chromosome, a string of DNA. Each chromosome contains a set of genes blocks of DNA, and each gene determines some aspect of the organism, like a color. In other words, parameters of the solution genes are concatenated from a string chromosome. In a chromosome, each gene controls a particular characteristic of the individual. The population evolved toward the optimal solution. The evolution based on the survival of the fittest. Genetic algorithms are well suited for hardware problems, where little is to know the underlying search space. So it is considered a robust search and optimization mechanism. Yeah, this semantic algorithm used in this work consists of the following steps or operations: initializing and encoding. The J started the creating of the random string, which represents each member in the population. Two is evaluation fitness. The fitness used as a measure to reflect the degree of the goodness of the individual is calculated for each individual in the population. Selection. And the selection of a process. Individuals choosing from the current population to enter a mating pool devoted to the creation of the new individual for next generation, such as the chance of the given individual to be selected to mate to proportional to the each relative fitness. This means that the best individual receives more copies in the subsequent generation, so that the desirable trait may be passed into their offspring. This step ensures that the overall quality of the population increases from one generation to the next. For its crossover provided a means by which valuable information is shared among the population. It combined the features of the two parent individuals to form the two children individuals that may have new patterns compared to those of their parents and plays a central role in the guess. The crossover operator takes two chromosomes and interchanges part of their genetic information to produce two new chromosomes. Mutation. Mutation is often introduced to guard against premature convergence, generally over a period of several generations. The uh, gen pool, gene pool tends to become more and more homogeneous. The purpose of a mutation is to introduce occasionally perturbations to the parameters to maintain the genetic diversity within the population. The replacement. After generating the offspring population through the application of genetic operators to the parent population, the parent population is totally replaced by offspring population. This is known as a no-overlapping generational replacement. This completes the life cycle of the population. Termination. The GA is terminated when some convergence criteria are met. Possible convergence criteria: the fitness of the best individual so far found exceeds a threshold value. The maximum number of the generation is reached. The proposed methodology is to generate test cases using a GA is as follows. Generate stimulus based on the feedback from the previously generated stimulus to cover areas which were not explored by a previously applied test. During each stimulus cycle, convergence tests are collected and sent input to the genetic algorithms and used as a guideline for next stimulus. The next stimulus will be more effective compared to the randomly generated one. Figure 4. The fitness function here is chosen to maximize the functional coverage percentage, where fitness functional coverage ratio. Simulation results show that coverage holes can be hit automatically with less effort and less time. Computational resource should be low. The results for some designs are reported in Table 3, where it is clear that using GA, we can reach 100% coverage in less time with less numbers of stimulus. Start simulation and coverage 100%. And this is the proposed GA methodology to speed up the coverage closure. Using genetic algorithm, there is no test redundancy. And the figure 5 is GA performance. This methodology collects the coverage data and analyze them, and then is assign a finished value to each solution. Table 3 is GA test-based generation result to get 100% coverage. The conclusion. The bug localization is processed to identify a specific locations or region of the source code that is buggy and needs to be modified to repair that defect. Bug localization cannot significantly reduce human effort and design cost. In this paper, another automated coverage-based functional bug localization method for complex HDL designs is proposed, which significantly reduces the debugging time. The proposed local bug localization methodology takes information from regression suite as an input and produces a linked list of suspicious parts of the code. Our methodology is promising the solutions to reduce required time to localize bugs significantly. Moreover, an online RTL level scan chain methodology is proposed to reduce debugging time and effort for emulation. Runtime modification of values of any of the internal signals of the DUT during execution can be easily performed throughout the proposed online scan chain methodology. A utility tool was developed to help ease this process. Our experiment showed that the area of overhead is neglected compared to the gain performance benefit, but IP design requires more compilation time. The main challenge in using constraint random test (CRT) is the manual analysis for a coverage report is needed to fit the untested scenarios, modifying the test cases to achieve 100% coverage. We need to replace the manual effort for by an automatic method or a tool that will be able to extract coverage report. Identify untested scenarios and add new constraint and iterate this flow until 100% coverage is obtained. In other words, we need automated techniques to automate the feedback from the coverage report analysis to test generation process. In this chapter, the implementation of this automatic feedback loop is presented. The automatic feedback loop is based on the artificial intelligence techniques called genetic algorithms. This technique accelerated coverage-driven functional verification and achieved coverage closure rapidly by covering uncovered scenarios in coverage holes. So there is. Okay, thank you for your time.